What we've got here is a direct current motor. What I'm going to do in this video is just talk a bit about what it is, how I built it, and how it works. So at first I'm just going to demonstrate the functionality. As you can see, it's connected to a power source. The power source is set to 2 volts. Once I turn it on, I just have to give it a little bit of a nudge, and it rotates quite rapidly. So in the next session I'll talk a bit about how I actually built this and how it actually works. One thing that we already know is that we know that when current travels through a wire, we get a magnetic field that's produced, and if I were to put that wire in the presence of an external magnetic field, we would actually get a magnetic force exerted on the coil or on the wire. So as we can see in this situation here, I'm going to actually run current through the wires, and I'm going to actually place this bar magnet, or I guess horseshoe magnet, around the wire, and we'll actually see the force that is exerted on it, and we can actually predict the direction that the force will be based on the right hand slap rule. Okay, so first of all, let's just verify that there is no force exerted on the wire as long as there's no current that actually runs through the wire. So we can see, just holding the magnet around the wire, that there's no actual force exerted. This is copper wire. Copper does not respond to magnetic fields. It's not ferromagnetic or paramagnetic. Okay. However, I can see that when I turn the current on, I'll try to do this to get a clear view. When I turn the current on, you see a very obvious deflection of the wire. So again, we can see that the wire is being shifted towards the back of the horseshoe magnet, a very clear force being exerted on the wire. Now, on this horseshoe magnet, this white piece of tape indicates the North Pole. We can use the right hand slap rule to actually determine the force direction. So what's going to happen is that my fingers are going to indicate the direction of the field, which is going to go from the North Pole of the magnet towards the south, like so. My thumb is going to point in the direction that the current flows through the wire, and then my palm will then indicate the direction of the force. The force will come outwards from my palm. So just looking at the setup that we just had there, I can see that I've got my magnetic field is going this way. I can see that the current, now this wire here is actually connected to the positive terminal, and this side here is connected to the negative terminal. So that means that we're actually going to have current that's going to be flowing upwards in this case. So from the positive up here down through to the negative. So keeping that in mind, my thumb is in the current direction, right? My fingers go from the North Pole towards the South Pole, like so, and then my palm then indicates the direction of the force, and I can see that the direction of the force in this case is going to be back towards the back of the magnet, and that's why we actually saw the wire move towards the back of the magnet. So just one more time. There we go. Quite a noticeable force. Now we can also try it, and we can actually flip the magnet over, so that now we've got the North Pole. The North Pole will actually be facing the camera, and what's actually happened to the magnetic field now, again from North Pole to South Pole, so it's going to be, I place my fingers in this direction from north towards south. My thumb is still going to go in the current direction, which is still going to be upwards, because this side is still connected to the positive, this side is still connected to the negative, so it's still going to be flowing upwards here. But now I've got to, okay, well my field is going to be from north towards south, and now I'd expect to see a force that's going to actually push the wire away from the magnet. Let's see if we actually do observe this. And we can see a very strong force that pushes the wire away. Let's see that one more time. A very noticeable force. Okay, so this is going to be the same idea as what makes the motor work. Alright, so let's talk a little bit now about the motor and what's going on with the motor, what the different components are, how it works. Now I've actually constructed this motor from a kit. This is actually the kit over here. So I had to assemble it, and what it comes with is it comes with some red and black wire. It also comes with the central sort of spindle. It's got a metal rod that actually goes through it. That's going to be the thing that actually rotates. Okay. Well, I guess it's going to be the axis of rotation. It's actually going to rotate about that, because we can actually see that if I get in here a bit closer, we can actually see that this plastic is actually resting on that metal that's sort of in between there. So we've got an axle in there, and it's going to actually rotate about that axis. These gray things here on either side, these are going to be the magnets. Okay, so that's going to be our external magnetic field. We've got obviously wires that are being wrapped around. We can see that I've actually stripped the wires on this side here, so we're actually getting an electrical connection, and of course those wires are ultimately connected to a power source as well. So essentially what we've got going on here is we've got current that is flowing through these coils. That's going to produce a magnetic field, right? And the way that we can actually determine that magnetic field is if I were to, let's say, model it with this pen. What's going to happen if the current, let's say that the current is going, so this is my right hand here. So if the current, let's say, is flowing towards the left, what I would do is I would take my thumb and it would point in the direction of the current flow. And my fingers, of course, you can see they're actually wrapped around the pen, okay, like so. You can see that's wrapped around the pen. That's going to indicate the magnetic field direction, okay. So we can see that in this case, if I'm viewing it this way on, the magnetic field would actually be directed around the coil. Remember that the pen is the coil, or the wire in this case, I should say. It's going to be the wire, and I can see that the magnetic field lines are actually going to go around in an anti-clockwise direction. Okay, so as soon as I pass current through the wire, I'm going to get this magnetic field that's going to be produced. Okay, now of course if I looked at it on the other side, right, from the back side, it's a bit awkward for me to hold it this way, but I can see that if I viewed it from this direction, obviously we would see that the magnetic field lines go around in the clockwise direction. But the important thing here is that when we get a current that flows through a wire, we're getting an associated magnetic field. Now, when the magnetic field that's produced when I actually run this current, so when actually running this current through the coil and it's producing that magnetic field then interacts with the magnetic field produced by the two magnets, and that then produces a force when the two fields are interacting. And we can actually determine the direction of the force based on the right-hand slap rule, just like I demonstrated over there with the horseshoe magnet. Okay, so maybe what we should do is I guess predict what's going on in terms of the forces. Now I'm just going to get a top-down view here. We can see that it's pretty close to a rectangle, which is going to be very similar to the sort of schematics that you'll see in questions that you'll be doing. And the red one, I've intentionally connected the red one to the red on the power supply, so that's going to be our positive. The black one is connected to the black on the power supply, so it's going to be very clear that this is going to be my positive, this is going to be my negative, which means that the current direction is going to actually go in through here, through the positive, right? It's going to then flow around the coil. Now this coil is wrapped around here about 10 times, okay? So I tried to make it as even as possible, so it's going to be about, if we look at a front view, we can see that it's about 5 or 6 times on the top side of the spindle. The spindle is just a thing that actually rotates, and about 5 or 6 times on the bottom. So I tried to make that as even as possible. The more even you can distribute the weight, and something is rotating, the better the rotation is going to be. Otherwise it's going to be a bit lopsided and it's not going to rotate as nicely. And so it's wrapped around there about 10 times. And ultimately what that's going to do is we're going to get a magnetic force that's going to be exerted on all 10 loops. So essentially by wrapping around 10 or 12 times, we're increasing the actual force being exerted 10 or 12 times. Okay? And so the current is going to come in through here, and you can see that we've got a bare wire right there, and that's going to be then connected to this bare wire, which is then going to allow the current to flow around the wires, and it's going to flow around, about the 10 or 12 different loops in there, and then it's going to flow out and then back through here, and that's going to complete the circuit. Okay, now this bit here is going to act as a commutator. We'll talk a bit about what the commutator is later on and what its purpose is, but for right now let's just determine the direction of the force that is being exerted. Now, in order to understand the direction of the force, of course, we need to know the direction of the magnetic field, and I actually don't know with this one what the actual polarity of the magnets are. It doesn't actually indicate the polarity of the magnets on them as far as I can tell. So what we're going to do is actually determine, I guess, using our third hand rule, what the actual polarity of the magnets is. Okay, so is it going to be? I know that they're opposite, so I know that we have either a north pole or a south pole that's facing the actual loops, and I've got an opposite pole on this side. So I know that when I bring these two magnets together, they're going to actually attract. They're going to attract each other because we have opposite poles. But I don't actually know if this is a north pole here and this is a south pole, or is this a north pole here and that's a south pole. I don't actually know. I didn't actually test them. Let's see if we can actually figure that out, just based on the way that the coil rotates. Now, I know in this case here that if I've actually done this, and we've sort of done a few demos here, and I know that it's actually going to rotate this way. So it's going to actually rotate. In other words, this side of the coil is actually going to go down, and this side of the coil is actually going to go up. So this side here is going down, and this side is going up, and of course we're getting a rotation. Okay? So in other words, we've got a downward force being exerted on this side of the coil, and I have an upward force being exerted on that side of the coil. So I'm just going to focus on this side of the coil right here that's closest to the camera, and talk about what's going on there. We'll also talk about what's going on either end on the left and right side, but let's just look at what's going on here. So we've got a downward force. Okay, I know that the current is going to flow from here, and it's going to be going this way. So remember, we're going to use my right hand slap rule, and so my thumb is going to go in the direction of the current flow, which is going to be this way. Now I don't actually know what the polarity of the magnets are, so I don't actually know the direction of the magnetic field. So remember, my fingers are going to go from north pole to south pole. Okay, so it should be from north pole on this side towards the south pole on my fingers. Okay, I don't know, is it going to go this way, which would indicate that we have a south pole on this side and a north pole on this side. Is it going to go like that? Well, no, because I actually know that it's going to rotate downwards, which means the force is going to be downwards, and of course the force is going to come out of my palm. Now, based on this, I can see, because my thumb has to point in the current direction, it's going to be this way, that I can see that it's actually, and it's going to be a bit awkward to do this with my right hand, but I can see that it's actually going to be a south pole here and a north pole there is going to create a downward force on this side when the current goes this way. So you have to sort of contort your hand around to see that. I can't really fully do it, but it's going to be a south pole on this side and a north pole on this side will cause this side to go downwards. There's going to be a downward force on this side of the coil. Now if you look on this side, if you follow the loop around here, remember the current is going through the red and it's going around here. Well, the current direction now is going to be this way. Remember that this side actually comes up, so we're going to get an upward force here. And so again, that would suggest that we have a north pole on this side and a south pole on that side. Okay, so again, my thumb goes in the direction of the current flow. My fingers are going to go from the south, so south side there, towards the north on this side like so, and that's going to then push this bit up. So this side is getting pushed up, this side is being pushed down, and we're seeing a rotation that occurs. Let's just see that rotation one more time, just to make sure that that is in fact what's going on. So I'll just give it a little bit of a push to get it going, and then we can see it takes off quite rapidly. So it is definitely that this side is coming up, and this side is going down, and we can see that we're getting that sort of rotation that's happening. I'll just shut this off quickly. Okay, now let's just talk quickly about what's going on with the right and left sides and the forces that are being exerted on them, or maybe there is no force. In fact, that's going to be the case. Okay, so let's again use our hand rules. Okay, so we've got the current, remember, going through the red wire is going to go through here. So my thumb is going to point in that direction. Now I get into sort of a weird situation now where my fingers have to point in the direction of the magnetic field. And so, okay, I'm trying to do it, and well, that means my fingers have to point in the same direction as my thumb. Not really sure how to do that, or possibly the exact opposite direction as my thumb. It's not going to be perpendicular. Okay, so what's going to actually happen is that if I've got field lines, if you can sort of imagine the field lines as going sort of straight across this way, or it could be straight across this way depending on what the polarity of the magnets is, I can see that the current is actually going to flow parallel to that. Okay, so the field lines are going to go again across this way, like so, but the current is actually going to be parallel to that in this part of the loop, and also of course on the left side in this part of the loop, and we're actually going to get no force that's going to be created. Okay, so whenever the current is parallel to the magnetic field lines, that means that we're not going to get a force exerted. The current has to have at least one component that's got to be perpendicular to the magnetic field. So I can see here, again, if I look back at these sides of the coil, so if my magnetic field lines go, again, across from my north or south pole, across the north or south pole, I can see that the current flow is going to actually be perpendicular to that. Okay? And so that's why we're going to get a force exerted on this one and this one, but we're actually going to get no force exerted on these two sides of the coil here. Alright, so I just want to talk a little bit about how the commutator works and the function of the commutator. So the commutator in this case is actually going to be these two wires here. Maybe actually I'll go around to this side and we can sort of see that I've got these two stripped wires here, and those are going to function as the commutator. So we'll talk a bit about why we have a split ring commutator and why it's necessary with a DC motor. First of all, we need to talk a bit about the forces that act on the coil, and we need to look at the coil when it's in different positions and different orientations. Now the orientation it's in right now is a horizontal orientation. So when I say horizontal orientation, I mean this. So we can see that the coil is oriented horizontally, and when I say vertical orientation, I'm referring to this orientation where the coil is oriented vertically. Okay? So we've already talked a bit about the forces that act on the coil when it's in the horizontal position. So let's have a look at the forces that act on the coil when it's in the vertical position. Okay? So we're going to use our hand rules to determine the force that acts on the top side of the coil. Okay? So I'm going to need my right hand for this one. As usual, my right hand slap rule. And so I know that my field is going to go this way. Right? So this is going to be the north pole. This is going to be the south pole of this magnet. So the field is going from the north pole of this magnet towards the south pole of this magnet. So my fingers, of course, indicate the field directions. They're going to point this way. Okay? I also know that the current is going to, remember this is connected to the positive terminal, so the current is going to flow through here, and it's going to actually go around in through this side of the coil, around the bottom, and then it's going to then flow back to the power source. Okay? So now that's not, I guess, the entire story, because there's actually going to be a split ring commutator that's going to actually break the flow of current at the top. So that's not entirely true with this setup, but let's just assume a situation where it was connected the entire time, that there's no break in the current. Okay? And we'll see, well, what would the forces be in that situation? Okay? Now, I can see in this case here, we've got my current is flowing towards the right, like so. It's going to be a bit difficult for me to get my hand in that orientation, okay? But it's going to be, and I'll maybe hold it to the side. So remember, the current is going in the direction of my thumb, the field is going in the direction of my fingers, and I can see the forces are going to be actually directed downwards on the top of the coil. Now the opposite is going to be true on the bottom of the coil. So the current is going to be flowing in the opposite direction, so I could use my hand rule again, and I can see, okay, again, my fingers point from the north towards the south, and on the bottom, of course, the current's going to be flowing the other direction, and so I can see that the force is going to be upward on the bottom of the coil. Okay, so what's going to be happening, again, assuming that the coil is actually connected to the power source when it's in the vertical position, which again in this situation it wouldn't be, but more on that later. If that was the case, we can see that the coil will be sort of getting squished. It's being pushed down on the top, it's being pushed up on the bottom, so it's getting sort of squeezed together, and those forces are not going to actually make the coil rotate. Now, in order for us to understand the function of a split ring commutator, I think it's important for us to understand, well, what would happen to the motor if we did not have a split ring commutator, okay? Now, obviously, as I've mentioned already, we do have a split ring commutator, and in fact, that's why the motor works as well as it does. So what I'm going to do is I'm going to actually take this setup apart, and I'm going to create a different setup where we don't have a split ring commutator, and we're going to talk about how the motion of the motor is going to be affected by that. Alright, so you can see that I've actually altered the setup here in a bit of a strange way, and it's not going to actually work very well for practical reasons, but I'm just trying to illustrate what would actually happen if we did not have the split ring commutator. So I've actually moved the two branches of the split ring commutator out of the way, and in fact nothing is actually, they're not connected to the power supply anymore. Instead, this yellow wire here is connected to the positive terminal of the power supply, and you notice it's connected to one side of the coil, and this green wire is connected to the negative terminal of the power supply, and it's connected to this side of the coil. Now, for practical reasons, you can see it doesn't really rotate well at all. The wires are actually in the way. What I'm trying to illustrate here is the function of slip rings. And when we have slip rings, and we're using them with a DC motor, it's going to cause some issues, because what's going to happen in that situation is that this side of the coil is always going to be connected to the positive, this side is always going to be connected to the negative, and the slip rings are going to be set up such that the motor can actually rotate, but it's not going to work very well. So let's discuss why it's not going to work well. Well, if we look at it so far, at just the initial setup, assuming that it was actually able to rotate, we can see that it would rotate just like before. This side here would go down, this side here would come up. Okay, so it would sort of start to rotate, perhaps. Okay, now what's going to happen as it reaches the top position, the vertical position, is that, well, remember what was happening here was the current was actually flowing in the anti-clockwise direction. Now, as it starts to turn to the vertical position, we can see that the current here, and remember the green wire is always connected to the negative terminal of the power supply, and maybe I'll just use my hand rules to try to figure out what's going on with the top coil here. So the current's going to be going this way, like so. Remember that this side here of my magnet is my north pole, this side is my south, so these are my fingers pointing from north towards south. My thumb is going to point this way because the current is going back towards the power supply, and so that means that the force is going to be up. So it's going to be sort of pushing, it's going to be sort of like spreading the coil apart, which obviously is not going to help the rotation at all. Now, let's keep following it along, and what's going to happen is I'm going to sort of reconnect either side of the coil just because is unable to rotate in the current setup. And I'm going to show you what's going to happen when it's at the next horizontal position. So it's gone from this horizontal position, and it's rotated here to the vertical position. And we're going to talk about what's going to actually happen as it continues to rotate over to the next horizontal position. Alright, so I've disconnected the wires just to make it a bit easier to rotate. Let's discuss what's going to actually happen and sort of put the pieces together. What's going to happen if we did not have a split ring commutator? So we can see in this situation, so we can imagine again that this side was connected to the positive terminal, this side is connected to the negative, so that means that we're going to actually get a rotation. Well, this side is going to be pushed downwards, this side is going to be pushed upwards, and then it goes over to the opposite side, and as we talked about before, now the current direction is actually going to go the other way, and that means the forces are going to reverse, and it's going to send the coil back the direction that it came from. And so you can sort of imagine this flip-flopping sort of that's going to occur. So it rotates this way, and then it goes to the horizontal orientation, and then the forces reverse, and then it goes back the other way. And you can imagine this sort of incessant flip-flopping back and forth. And it makes complete sense to think of it this way, but in fact this is not what would be observed. what would actually be observed is that initially it would start to rotate like so, and remember that at the top position the forces that are exerted don't actually cause it to rotate or to stop rotating. So it's the coil's momentum would carry it past that point, but then as soon as it goes past the vertical position, now we're going to have components of the force that are going to be in the opposite direction. Okay, just a component of the force, but that component is actually going to be strong enough to actually stop the coil, probably at around this position, which is just past the vertical orientation. Sometimes it'll go a little bit further, but not much further. And it's going to be enough to stop it there and to then already force it back the other direction. And then what's going to happen is that it's going to again go to the vertical and just past the vertical, and now the forces are going to have components that are going to be strong enough to stop it, and we get sort of an oscillation about the vertical position. And over time, as the spindle loses more and more energy, then the amplitude of the motion will become smaller and smaller and smaller, and eventually it'll just sort of stop and it will kind of vibrate there, and that's sort of what you'll see. So it'll actually be even more useless than just our sort of flip-flopping motor. We're actually just going to have a situation where it's sort of just vibrating sort of very quickly in place, and that will be the way that our motor functions. Okay, now let's talk a bit about how the split ring commutator will actually address this problem. So what you'll notice is that I've actually marked off either side of the coil with a different color post-it note. So I've marked off this side of the coil with a green post-it note and this side with a blue one. Okay, and what I note is that, remember that this wire here, this red wire, is connected to the positive terminal, which is ultimately connected to this side of the split ring commutator. And again, when I say the split ring commutator, I'm talking about these two bare wires here that ultimately connect to either side of the wire. And I can see that this side of the commutator is always connected to the red wire. That means this side of the commutator is always going to be positive. And I can see that this side is always going to be connected to this black wire, which is connected to the negative terminal. So this side of the commutator is always positive, this side of the commutator is always negative, and that's going to be important. Okay. Now again, I've marked off either side of the coil with different color post-it notes. And so I can see that right now, I can see that the green side of the coil, where this green post-it note is connected to the positive side of the commutator, and I can see that the blue side of the coil is connected to the negative. What that means is that current is going to flow around the coil in the anti-clockwise direction, right? Just like it's been doing, just like we've been talking about. Okay, and so we know that the force that's going to be produced in that situation is going to cause it to rotate. Well, let's see, we've got, let me just remind myself here. So we've got like this. Using my hand rule, I can see that this side here that's closest to the camera is going to get pushed down, and this side that's away from the camera is going to get pushed up. And we get that rotation. Okay, so that's the forces that are going to be created in this situation. Okay, so what's going to happen is, okay, so we're going to, this side goes down, this side comes up. Now notice that in the commutator setup, we can actually see, just by looking very carefully here, I can see that these are the either sides. Maybe I'll get a better angle here. These are the two sides of my commutator, and I can see that this side of the coil is directly in between the two. And in fact, the contact has been broken at this point. So in actuality, what's actually happening at the top of the motion, right, when it's in the vertical orientation, is that just for a brief instant, there's going to be no current that flows through the coil. Now this is actually okay because the coil's momentum is going to carry it over, but just very briefly at the very top of the motion, we're actually losing the connection. Okay? Now you might say, well, why don't we have a situation where we are not losing any electrical conductivity? Well, in that situation, well, first of all, there's two problems with that. The first we talked about earlier, which is that the force that will be produced in this situation won't actually add to the object's rotation, so there's really no benefit to it. And the second is that if it was connected, we would actually get a circuit that would be connected, actually be a short circuit, would be connected here, and actually the current wouldn't flow through the coil. It would actually just flow straight from this side of the commutator through here to this side of the commutator and back to the power supply. So there's really no benefit for that to happen. Now, as it rotates through, we can see that the blue side is now touching the positive terminal. So remember how it was. Maybe just rewind that back. So the way that it was before is that the blue side of the coil is connected to the negative side of the commutator, and the green was connected to the positive. And so current was flowing this way around the coil. Okay? Now, what's going to happen after half a revolution is that now the blue side of the coil is connected to the positive, and the green side is connected to the negative. Okay? And again, what's going to happen is we're going to have current that's going to flow around this way, and well, we're going to get the same forces. It's going to actually keep it moving in this direction here. And so essentially what's going to happen is that the forces that are produced as a result of because of the split ring commutator, and because we're ensuring that current is always going to sort of flow around this way through the loop, is that we're always going to get forces that are in the same direction, in other words, down on this side and up on this side, and so we get a constant rotation of the coil. And obviously that's going to be a lot more beneficial to us, especially if we're talking about something like a fan, or if we're talking about a drill, or anything that has a motor in it where we need that constant rotation. Obviously we're going to want to have a split ring commutator in there when we're using direct current.